Hello dear students, in this video on chapter 6 of a triangle, we are going to learn about the similarity of a triangle. What are the properties based on which we can say mathematically that a particular shape is similar to another shape. So this chapter is concerned about a triangle. So we'll study various theorems based on which we can prove that a particular triangle is similar to another triangle. And we will also study and learn about what is the relation between the areas of two similar triangles. And in the past, we have already studied Pythagoras theorem. So at the last, we'll study and learn about more about Pythagoras theorem. So, in our day to day life, we often use the word similar. When we have a friend, somebody asks, why do you, do you have that boy as your friend? So, we'll say, oh, he's very similar to me. He has similar interest. We both have interest in studying mathematics or playing football. So, word similar is well known to us mathematically. Now we will learn. So if you see the figures, what do you see? These two boys, they look quite similar. The flowers similar in color, the posture similar. So now we will study what does similarity means in mathematics. So you see here the two triangles. What do we say after looking at these two triangles? They look similar. Similarly here, this one is larger, this one is smaller, but they look similar. This rectangle and this rectangle, they look similar. Similarly here, this pentagon, small than large, this triangle. So all these shapes, whether it is a triangle or a rectangle or a pentagon or a triangle, these are all examples of shapes which are similar. And what do you say about certain shapes like a square? Irrespective of dimension of square, all the squares are and will be similar. Similarly, circle, irrespective of what radius of that circle is, whether it is small or whether it is large or very large, all these circles will be similar, irrespective of the radius or diameter. So certain shapes will always be similar. Square, circle, and can you think of some other examples in a triangle? Because this chapter is on triangle. See, all equilateral triangles will be similar. So I think you have now understood the meaning of similarity. So unlike congruence that we studied in class ninth, similarity has to do more with the shape, not with the size. So now we come to the definition of similarity. So two polygons are similar if two polygon having same side, same number of sides are similar if they satisfy two conditions. First, corresponding angles are equal. And second, corresponding sides are proportional. We are not saying equal. So what it should be equal is corresponding angles, and corresponding sides should be proportional. So this is the basic definition based on which we can say whether any shape, whether it is a pentagon, octagon, or any shape, if the two shapes will be similar or not. So we'll have only these two as the criteria. We'll see whether the angles are equal or not, corresponding angles are equal or not, and whether corresponding sides are proportional. So I've taken an example from the NCRT book. We have these two quadrilaterals. So you see the corresponding angles 85, 85, 70, 70, 100, 100. The corresponding angles of these two quadrilaterals are equal. So these two quadrilaterals satisfy the first condition that corresponding angles are equal. Now let us see the sides, dimensions of the sides. This is 2.4, this is twice 8, 4.8. This is 2.1, this is twice it, 4.2. This is 2.5, this is 5. This is 1.5, this is 3. So the sides are in the ratio 1 is to 2, corresponding sides. I cannot say compare this side with that side, or this side with this side, or this side. So I have to see the corresponding sides contained by these equal angles. So these two quadrilaterals satisfy the second condition also, that corresponding sides are proportional. They are in the ratio 1 is to 2. So we can with certainty say that these two shapes, quadrilaterals, are similar. So now you can easily solve exercise 6.1. All circles are what? Congruent or similar? They cannot be always of the same radius, so they will be always similar, which we have studied here. All circles are similar. Similarly, all squares are also similar. Triangles, isosceles or equilateral, which are similar, all equilateral triangles, because they will always have all the angles as 60 degree, and sides of course will be proportional. Two polygons of the same number of sides are similar when their corresponding angles are equal and their corresponding sides are also equal or proportional. No, it is proportional. Give two examples of pair of similar figures, non-similar figures. This you can give. Whether these quadrilaterals are similar or not. So we to check the similarity, we'll go to our to these two basic criteria. Corresponding angles should be equal and sides should be proportional, not equal, but proportional. So we see the sides here are proportional. 1.5 times 2, 3, 1.5 times 2, 3, 1.5 times 2, 3. These sides are proportional. But what about the angles? Here we have 90 degree, here it is more than 90 degree. Here 90 degree, it is less than 90 degree. So the corresponding angles are not equal. So these two shapes, although they satisfy second property, corresponding sides are proportional, but they don't satisfy the first property that corresponding angles are equal. So here corresponding angles are not equal, so hence these two quadrilaterals are not similar. So we now come to the similarity of triangle. So triangle, what is the definition of a triangle? Triangle is the smallest polygon having three sides. It's a closed figure. So it's a polygon. So the same rule applies here also, that triangle will be similar if its corresponding angles are equal and corresponding sides are proportional. So if corresponding angles of two triangles are equal, then these two triangles are known as equiangular triangle. So in a equiangular triangle has corresponding angle equal. And there was a famous Greek mathematician, Thales. He stated one uh, remarkable truth or property about equiangular triangle, that their sides will always be proportional. And he used basic proportionality theorem to prove that equiangular triangles always have their corresponding sides in the same ratio. When I say proportional, I mean that the corresponding sides are in the same ratio. So now we will go to basic proportionality theorem. So we'll do this activity which is given in your NCERT book. So draw a triangle, sorry, an angle. So these are the two lines. So let us mark a few points on this line. That is this called, at this point be A, and this Y, and this is X. So let us mark some point on X. Let this point be P, Q, R, and S. So from point say S, we select any point on line AY. Let this point be B. Let this point be B. So we join these two lines. Oh, sorry, I mean, yeah, we join these two points. Now let us draw lines which are parallel to BS. So we draw a series of lines parallel to each other, and let us give them some name. So this is RC, this line is RC, this is QD. So these we have also formed a series of triangles. One, this triangle, and this triangle. So what does the basic proportionality theorem? It states that these that equiangular triangles have corresponding sides proportional. So this angle is equal common for all these triangles. And if we see, if we take these two triangles ARC and ASB, then their corresponding angles, these are equal because these two lines are parallel, so their corresponding angles are equal, and this angle will be equal to this angle. So in these two triangles ARC and ASB, corresponding angles are equal, and if we measure these sides AC divided by AB and AR divided by AS, we'll find that the ratio of these sides is same, which is what our basic proportionality theorem states, or Thales theorem states. So this is our basic proportionality theorem, or Thales theorem, that equiangular triangles have corresponding sides proportional. Now we go to the first theorem. The theorem is, if a line is drawn parallel to one side of a triangle and it cuts other two sides at two distinct points, then the two sides are divided into same ratio. So what does this theorem states? It states that suppose we have a triangle, and if we draw a line parallel to one side, any one side we can take, other we can take this to this side, this side, this side. Ah, so we take we draw a line parallel to this side. So let us name this triangle. This triangle VABC. So a line is drawn parallel to one side of a triangle, and it cuts other two sides in two distinct points. See, this is one distinct point, and this is another distinct point. So this diagram satisfies these two conditions, that a line is drawn parallel to one side of a triangle and it cuts other two sides in two distinct points. Let us then name them D and E. So the ratio in which these lines are divided is the same ratio. That means AD by DB is equal to AE by EC. This by this is equal to this by this, and it is given that this line is parallel to this line. So this is what this theorem states, but we need to prove this theorem, whether what the theorem states is correct or not. So what we will do is we'll we'll join D and C and B and E, and we'll draw perpendicular these two perpendiculars. Let us name them F and G. So we have to prove this is what we have to prove, and what we are given is DE is parallel to BC. Now let us find out area of a triangle ADE. This area, this triangle ADE. So if we take this base, so area of a triangle is half base into altitude. So area of triangle ADE considering base AE is equal to half base AE into altitude dg. Similarly, if we take this as our base, AD as our base, so the area of triangle ADE can also be written as AD into FE. FE is an altitude. So what we have drawn is we have drawn these two altitude. One altitude, one perpendicular from D on AE, another perpendicular EF on AD. And we have also joined D and C and B and E. So again area of a triangle ADE, so again the area of triangle AD considering the base AD is half base into altitude FE. Now we will find the area of this triangle, this shaded triangle. See, can you see this DBE? This is the base, DB is base, and FE is altitude. So area of this triangle AD DBE is equal to half base DB into EF. A for FE. So now we'll find the area of this triangle. This one. Where I have put dots. Considering this base EC and this is an altitude. So area of a triangle EBC will be EC into DG. EC is the base and DG is the altitude. So why we have taken this triangle and these bases? Because what we have to prove is AD by DB is equal to AE by EC. So we should get these segments or these line segments in our equation. We are getting AD DB AE EC. AD DB AE EC. So now what we will do is we divide this one, this I call name. Let us divide equation 1 by 4 and 2 by 3. So let us divide 1 by this 3. Is area triangle ADE, 2 divided by. So this becomes ADE divided by DEC, 1 by 4. So this cut out, half cuts, and we get AE by EC. So we get AE by EC. Similarly, if we divide equation 2 by equation 3, so what we will get? So we divide equation 2 by 3, we get area AD divided by area of DB is equal to half AD into FE divided by height BB into FE. So this becomes FE cut. These are positive numbers, half and half cut. So we get AD by DB. But we observe that area triangle DC is equal to area of triangle DB. Why? This is because, see, these two are parallel line, DE and BC. And these are the two triangles based on the same base and between the same parallel line. So, areas of triangle on the same base and between two same parallel line are equal. The reason is simple. See, if we find the area of DEC, and suppose if I draw this as an altitude, it goes outside these triangles. This is our altitude. So for this triangle, it is DE into this altitude. For this triangle DEC also, it is DE into this altitude, because this altitude remains the same for both. It is the distance between the two parallel lines. So area of these two triangles will anyway be equal. So if this is equal, then what does that mean to us? This means that AE by EC is equal to AD by DB, because this area is these two triangles are common, and area of DEC is equal to area of triangle DB. So what we get ultimately, AE by EC, and this is what we wanted to prove. AD by DB is equal to AE by EC. That these the 2 points on which this line divides the sides of triangle are divided in a proportion. So AE by EC, AD by DB is equal to AE by EC. That means the sides of the triangles are divided in the same ratio. And this is what this theorem is. If a line is drawn parallel to one side of a triangle, then it divides the other two sides in the same ratio. AE by EC is equal to AD by DB. So we have proved this theorem that if a line is drawn parallel to one side of a triangle, then it cuts, and if it cuts the other two sides at two distinct points, then these are divided in the same ratio. Now we will prove the reverse of this theorem. So we will prove that if a so we will prove now this theorem that if a line cuts two sides of a triangle in the same ratio, then it is parallel to the third side. So let us draw it. So let this be ABC triangle, and this be a line which so we have line D which cuts AB and AC at two distance points D and T, such that AD and DB and AE and EC are in the same ratio. So we are given, this is what we are given, that AD by DB is equal to AE by EC, and we have to prove that DE is parallel to BC. So first we assume that DE is not parallel to BC. So if D is not parallel to BC, then we will have some point E dash such that D dash will be parallel to BC. So we assume that D is not parallel to BC, but we have DE dash. So DE dash is parallel to BC. But by the previous theorem, we know that if a line is drawn parallel to one side of triangle and it cuts other two sides at two distance points, then the two sides are divided in the same ratio. So here we are given DE dash is parallel to BC, and it is of course dividing ABC triangle at two distinct points D and E dash. Then these 2 points, they divide the two sides in the same ratio. This is what the first theorem says. So that means that AD by DB is equal to, the ratio of AD to DB is equal to AE E dash by E dash C. So this we get from theorem 1. Let this be equation 2, and this is our equation which is already given, equation 1. So what we can deduct from this equation 1 and equation 2, that AD by DB is equal to AE by EC by equation 1, and by equation 2 it is AD by DB is equal to AE dash by E dash C, sorry. So that means that A dash E divided by E dash C is equal to AE by EC. Their ratio should also be the same. So from 1 and 2, equation 1 and 2, what we get, AE dash. So let us add 1 to both sides of this equation. So we add 1 on both the sides. So what we get? So if we add 1 on both the sides, we get AE dash plus E dash C by E dash C is equal to AE plus EC divided by EC. This comes out to be, so we get AC by E dash C is equal to AC by EC. That means that E dash C is equal to EC. Now that implies that E dash and E are the same points. See, we had assumed that D E dash is such a point that D dash is parallel to BC, but E dash is the same point as a point E. So that means that D is parallel to BC. So this is what we have proved. Now let us do some exercises from the chapter 6. So we are given that DE is parallel to BC, and we are required to find EC. So if D is parallel to BC, we know from theorem 1 that if a line is parallel to third side of the triangle, then it divides the other two sides in the same ratio. So AD by DB is equal to AE by EC. One which we have studied, what we get, AD by DB is equal to AE by EC. So now let us input the values provided in the figure. So we get 1.5 by 3 is equal to 1 by EC. That means EC is equal to, so we get EC is equal to 2 centimeter. Similarly, we can solve this question also. We just need to input the values provided in the figure. So we'll get AD is equal to will, will be equal to 1.8 divided by 5.4 into 7.2. That comes out to, so it is 2.4, the answer for subsection 2. Now let us solve the question 5. As questions 2, 3, 4, they are very easy questions. So we are given that DE in this triangle PQD, this one, DE is parallel to OQ, and in this triangle PQR, DF is parallel to QR or O, sorry, DF is parallel to OR in the triangle POR. So from this first triangle, what we will get? DE by E. From this triangle PQO, we get P by EQ is equal to PD by DO. And from triangle POR, we'll get PD by DO is equal to PF by FR. That means P by EQ is equal to PF by FR. So these two ratios are equal. That implies that in triangle PQR, P PE by EQ is equal to PF by FR. That means that EF is parallel to QR. From theorem 6.2 of the test or theorem 2. So EF is parallel to QR because line EF is dividing the two sides of the triangle in the same ratio. And that is possible only if EF is parallel to the third side. So we have proved